field and the electric potential in electrostatics. What is electrostatics? Electrostatics is a space where the charges are present at rest. Charges are not moving, they are at rest. The charges may be a single charge or multiple charges, and the charges may be of same type. All are negative charges or positive charges, or mixture of different types, both negative and positive charges. That is a space. In that space, we need to understand, we need to estimate the electric field and potential in that surroundings or in that space, at every point in the space. Now, the subject or the charges of study is this type of charges. It is electric dipole. The charges are electric dipole. There are only two charges. One is negative charge, other is positive charge. What is electric dipole? We need to understand what is the meaning of electric dipole. Electric dipole means there are two charges which are separated by a distance, that is negative charge and positive charge. That is a dipole. These two are separated by a distance. The distance is 2L, of course. L plus L is the midpoint of the dipole. The charges are, one is there is negative charge minus Q, the positive charge. The magnitude of the charges are same, that is Q, and there are different types, minus and positive. These two charges are separated. The distance is infinitesimally small distance, extremely small distance, extremely small difference, small distance between these two charges. So this is called as a dipole, electric dipole. Example, very good example for electric dipole is a molecule like this. HCl is a molecule. It is forming by a chemical bond between H and Cl. Look at that H and Cl. There are quite a larger electronegativity difference. Electronegative difference means one is attracting electrons more, other is attracting electron less. After the chemical bond formation between H and Cl, the bonding electrons or bond pair electrons are attracted more towards Cl, lies more close towards Cl than H, resulting in the polar bond. This chemical bond is a distance of separation between this and this. So this results, that is partially a negative charge, a partially positive charge. A small amount of positive charge arises at this point, that is a point of atom, and a small amount of negative charge arises at this point, that is at this point of atom, that is point charges. So it's a very good example for dipole, electric dipole. That is, the amount of charge is this amount of charge is minus Q, this amount of charge is plus Q. Of course, it is written in reverse, doesn't matter. So that is called as electric dipole. If the molecule like this or electric dipole like this is present in a space, so there arises electric field and as well as electric potential in the space surrounding that dipole, surrounding that molecule. So we need to calculate, very important to estimate that is electric field and electric potential at every point in that space. That is, you are estimating using a mathematical expressions. and those mathematical expressions need to be derived. That is why the subject is derivation of those expressions. So we need to express what is our derived expression for electric field at the point. I have taken 2 points. There is a one point, there is another point here. These 2 points in the space around the electric dipole. So where the point is lying? So now it is lying along the straight line. That is a line, straight line drawn along this line of what is that dipole. This is a line of dipole. When you draw a line like this straight line, so extending this side and this side as well as, that is called as line, straight line is called as axis of dipole. If you draw a straight line along the line of dipole, on either side is a long straight line, it is called as axis of dipole. That is the center of dipole. That is, so this is total length is 2L, is L this side, L this side. So if you draw a straight line perpendicular to the what is that line of dipole, that is the line of dipole. If you draw a straight line perpendicular to this at the center of the dipole, this is center of dipole. This line is called as equatorial line of dipole. Okay, there are 2 lines you drawn. One is along the axis, other is along equatorial. That is equatorial line and axial line. I have taken the point along the axis, anywhere along the axis, either this side or away from this or towards this, either this side or other this side, doesn't matter. I have taken the point along the axis of dipole, this is the point, and one more point along the equatorial line, anywhere along the line, either this side or this side. I have taken the point here. So at this point, first you have to calculate. Only at this, a point along the equatorial line and a point, any point along the axis of the dipole. You have to derive the expression for electric field and electric potential. So there are 4 derivations. So what is the electric field at this point? There is one derivation, and electric potential at the same point, another derivation. That is derivation number 1, derivation number 2 for this one. And derivation number 3, that is along the equatorial line. What is the electric field at this point? And electric potential at this point. So electric field at this point is this derivation. That is one more derivation. And electric potential at the same point is another derivation. 4 derivations. So we get these 4 mathematical equations for the estimation of electric potential and electric field for this point and this point. So let us see what are the details of the derivation. That is, derivation is electric field at a point along the axis of dipole. The point I have taken, derivation. We need a diagram like this. That is electric dipole. This point as minus Q, this point as positive plus Q. That is amount of charge, amount of charge. The charge nature is minus, charge nature is plus. Now the distance of separation is 2L. That is the midpoint of the dipole. This dipole is characterized by a quantity is called as dipole moment. Dipole moment. What is dipole moment? This dipole moment is a vector quantity. Dipole moment is a vector quantity. So every dipole, whether a molecule or electric dipole, is characterized by dipole moment. Dipole moment is a vector quantity, both magnitude and direction. The magnitude of dipole moment of this electric dipole is P. This is called dipole moment. The magnitude is Q into 2L. the amount of charge, either this or this, both are same, into distance of separation 2L. It is Coulomb meter SI unit. That is the magnitude of dipole moment, and the direction of dipole moment is along this line. What is that? Along the axis of the dipole, but from negative to positive, from negative charge to positive. This is the direction of the dipole moment. So that is what the quantity used to describe or characterize a dipole of a material. So now we want to derive the expression for electric field at this point. You know, using what is that law? What is that electric field at this point? Look at this. There are two charges along this line. So this is plus Q and minus Q. So therefore, electric field at this point, because of this charge as well as this charge. So it is a vector sum of those two electric fields. So there are two electric fields produced at this point. One is because of this charge, other is because of this charge. As you know, write a definition for electric field at any point. Recall the previous one using Coulomb's law. KQ divided by x squared. K means Coulomb's constant magnitude of charge. That is a unit positive charge. That is Coulomb's law. This one. KQ by x squared. What is x? Distance of separation of the point and the charge. This is the distance of separation. X squared here. Using these definitions, let us write the equation for electric potential at this point using this, electric field at this point using this charge, electric field at this point using this charge. So write this. E1 is electric potential at this point because of this charge. That is, plus is there, plus K, Coulomb's constant, Q is plus. Divide by x square means that is the distance of separation. This distance you can write in terms of these two values, R and L. What is R? Distance between the center of the dipole and the point, R. There is a distance between point and this. So this is what is R minus L. From this here one straight line. So this distance is this minus this. R minus L whole square. Similarly calculate, that is field at this point, that is because of this charge. Minus Q is a charge, Coulomb's constant, minus Q, that is Q divided by x square. What is x square? The distance between this and this is x here. So here the distance between this and this plus this, R plus L. The total distance between this point and this is R plus L whole square. These are the values, mathematical expression. Then the resultant or the vector, the net vector is a vector sum of these two. That is, vector sum is E1 plus E2. That is, E1 because of this, E2 because of this. So substitute for this. This is equal to, this is the one for this. Minus is then minus. Simplify algebra, simple algebra, taking LCM and simplify, you get this now. And this minus this numerator, expand it, and this is this into this whole square. This becomes R square minus R square whole square, and gas cancels. What is the remaining here? 4 into RL. KQ as common factor taken out. 4 into RL. Rewrite this. 2KR. 2 into 2. 2KR into Q into 2L. Because Y equal to 2L is P. We need to be substituted. That is why you can rewrite like this. And this becomes 2KR divided by P. Divided by denominator remains same. Now this expression. And you have to make some approximation because I said L is very small comparatively, very small to this R, because I told you the distance of separation is infinitesimal small, extremely small. If 2L is small means L is also very small. That means R because I'm talking about the molecule, this bond is very small in angstrom. R is far greater than L. Therefore, R must, what is that? L is 0. Assume that 0 L is, because remaining is R to the power of 2. R to the power of 4 divided into R is there, cancel remaining R cube. 2 Kp divided by R cube. So, what is that? Net electric potential, that is net electric field at this point. Net electric field is vector sum of two vectors, that is by this as well as this. So you have done by mathematical simplification. The net electric field at this point is 2Kp divided by R cube. P is the dipole moment of this electric dipole, and this electric field, that is electric field at this point. So this electric field is positive direction, it has both direction and magnitude. Magnitude is this. And direction means what is the direction? Because of positive, this is the direction. Negative means this is the direction. So in this case, negative says this is the direction, positive means this is the. So final value is positive, the direction of the E is along this. That is direction. And direction of this is the direction. So by this, you see that direction of the electric field and direction of dipole is same. That is, direction of electric field, direction of dipole is same direction. So represent this is a vector. Magnitude is this. Magnitude of this is Q into 2L. So that is a mathematical expression for electric field at any point along the axis of a dipole. It is 2 into Coulomb's constant into dipole moment of the dipole divided by R cube. What is R cube? The distance between the center and the point. That is R cube. That is the first derivation you have got. What is the next derivation? For the potential at the same point. For the derivation of potential, write the definition, mathematical definition for the potential at this point. Recall the previous class. Write the definition for potential at any point. Just recall the mathematical definition. There is a mathematical definition, field at any point. And what is the potential at this point? This is a potential. What is that? V stands for potential at any point is equal to K again. What is K? Coulomb's constant into magnitude of charge by which potential arises at this point, divided by a distance of separation. Recall the previous one definition. Using this definition, right, there are again two, what is that, potential arises. Two potential, one potential because of this, other potential because of this at the same point. That is V1, V2. Right, using the definition, it is K, Q is plus Q. X means distance of separation is R minus L. R minus L. Similarly, V2 is equal to K into Q. It is minus Q. That is minus Q. K divided by distance of separation is this. That is R plus L. Total length. Then these two are raised as summation. That is, these scalars suppose. Sum of the scalars, that is net potential at this point is sum of the two quantities. This plus this. This is positive, this is negative. Look at this. Again simplify using LCM. LCM is this into this, cross multiply these two. Simplify, you can know KQ2L divided by R square minus L square. Rewrite this is P, dipole moment. Q into dipole. This is dipole moment. And again approximation, this R is very large compared is to L. That is the case. Almost this is equal to R square. So Kp divided by, that is P. Kp, this word is P. Kp divided by R square. So that is a mathematical expression, mathematical definition for the net potential at this point. Here potential, because of these two charges, the net potential at this point is Kp divided by R square. What is K? Coulomb's constant into dipole moment divided by R square, distance of surface, that is distance between the point and the center of dipole. Mathematical definition for this. This is a mathematical definition for this. Let us go to electric field at the same extension. You go for the other derivation. Now let us derive field and potential at this point. The point is along the equatorial line. So there are two charges. These two charges experiences what is that will affect at this point. So there are two effects, that is sum of the two vectors. That is first field. Let us write this is what is that vector, that is a electric field at this point because of the charge. This is electric vector. Direction electric vector, it is what is positive charge. This is a direction. Is away. This pushing away from this. There is a direction vector. What is direction vector of this is because of this Q. This is positive charge, unit positive charge here P. This is a direction vector minus. Look at the direction. This is a direction. This is a direction. So vectors here, look at that. There are vector direction. This is actually vector. This is a direction. These two vector. This vector due to this. This vector is due to this. Direction of the vectors. E1 is the field at this point because of this charge. E2 is the field at the point because of this charge. E1, E2. The directions are here. Here there is a vector originating from this point. This vector originating from these two points. These two vector. So these two vector is sum of these two vector is a resultant vector or net vector. How do you sum this? Not simply adding that. The addition of vector is actually using this mathematical addition of vector like this. So vector addition of parallelogram, that is a derivation is required for this. So addition of these two vectors like this, it's the same thing. What is that? Where this is a point here. It is the same representation vector. This is vector, that is A, B. It is called as E1, E2. The resultant vector is what is that? Diagonal of the parallelogram R. That is called resultant vector you get. That is a resultant vector. That is a diagonal of parallelogram. So this is the angle is between these two vectors, eta. The angle between these two vectors is, it is between this and this is theta, between this and this theta, that is theta is same as this because it is parallel to this theta. That is total angle is 2 theta between these two. So derivation, we don't want derivation, we have the formula for the vector addition of these two vectors like this, with the angle like this. We have standard formula. That is resultant of these two vectors we need. That is these two vectors give a net vector. The resultant vector is, this is the formula for this. Recall the standard formula. R is equal to square root of A square plus B square plus 2AB into cos of the angle subtended by these two vectors pi. So that is the vector I need to find out. Electric field at the point is the vector. This is a vector. Electric field at this point due to these two charges is this vector. That is one net vector is equal to. So that is the one substitute. The same thing rewrite this formula for these two. Resultant vector or net vector is field here, electric field. E1 square E2 square plus 2 E1 E2 cos. Total angle is cos 2 theta. Angle between these two vectors. Now this is the magnitude of the field by this. This is magnitude of the field by this. Estimate the magnitude of this. This is a vector direction. That is vector quantity. So using this Coulomb's law, what is recall the definition? The definition is the same thing, k cube by x square. For this one, electric potential at this point due to this is Coulomb's constant plus q divided by distance of separation r1 square. r1 square. Look at this is a triangle, right angle triangle, 90 degree. So r1 can be written as r square plus l square because Pythagoras theorem. R square plus L square. This is the one. So E1 is equal to, this is a mathematical formula. Similarly, calculate what is that? Write the expression for E2. That is E2 because of field at this point by this Q. The same formula, K into Q divided by, that is amount you are calculating, not the direction, the magnitude. Need not require negative sign. K Q by R2 square. K Coulomb's constant Q by R2 square. What is R2 square? Rewrite in terms of these values. Pythagoras formula R square plus L square. Look at that E1, E2. Magnitude of what is that? Magnitude of E1, E2 remains same. E1 is equal to E2 is equal to same. So that represents what is that? E1, E2 remains same. The magnitude, let us write the total vector. It has both magnitude and what is that? Direction. So that is E1 is E, E2 is E, E1, E2 is square cos 2 theta. So simplify this. E square means 2 E square plus 2 E square. 2 E square common. Take out 2 E square common factor. Remaining is 1 plus cos 2 theta under square. And recall that what is that 1 plus cos 2 theta trigonometry formula. 1 plus cos 2 theta is equal to 2 cos square theta. That is identities, formulas. So this is 2 cos square theta. Now we have 2 square, 2 into 2, 2 square, E square into cos square. Root is there, it's cancel, it is what is 2E cos theta. So what is E net? E net means potential is field, electric field at this point because of these two charges. Net electric field at this point is 2E cos theta is a vector quantity. 2E cos theta. So magnitude is this one. This magnitude. Cos theta. Cos theta represents the direction of the vector. For this, what is that? Theta. What is theta in terms of this? That is, theta is take cos theta. That is adjacent by hypotenuse. Cos theta is equal to adjacent by hypotenuse. So cos theta is equal to adjacent by hypotenuse R1. R1 is R square plus R square, that is root, that is a Pythagoras theorem again. That is R1 square. R1 is equal to this. Put this and this into equation, simplify, you get this. To the 4 of 1 to the 4 of 1 by 2, that is R plus R square plus R square whole square, over to the 4 of 1 to the 4 of 1 by 2, that is 3 by 2. Okay, this becomes QL2P becomes P. Dipole moment K into P divided by this. So this is L again, approximation. This L is extremely small. There are almost 7. What is that? R square. R square to the power of 3 by 2, that is R cube. Put to cancel. Kp by R cube. That is a net electric field. So net electric field at this point. Net electric field at this point because of these two charges is Kp by R cube. Look at this field at this point. There is a magnitude of the electric field. What is the direction? Look at the direction already here. What is the dipole direction? This is the direction. They are in opposite. Electric field at this point, the direction is opposite to this dipole direction. Therefore, direction of electric field is opposite to the direction of dipole moment. Dipole moment direction is this is the direction, and this is the direction of the electric field at this point. They are in opposite direction. Magnitude and direction, mathematical expression. So that is the field at this point. Now the final expression is what is the potential at this point? The same definition for potential. What is that? V is equal to kq by s. Right? What is the potential? V1 because of this charge and V2 because of this charge. Using this equation, write what is V1, what is V2. V2 is equal to K plus Q divided by R1. That is plus KQ divided by what is R1? R1 is Pythagoras. Using Pythagoras theorem, what is the root of R square by R square plus R square. Similarly, cathode is write the expression for V2. V2 is potential at this point by this. It's same as it is Q is minus Coulomb's constant divided by X is R2. Distance of separation is R2. Rewrite this as in terms of these two. That is R square plus L square under root. So net potential is, what is net potential is V1 plus V2. V1 plus V2. Substitute this. This is positive, this is negative. Plus minus of this. Look at this. The first term and the second terms are same. So this minus this is equal to 0. So net potential at this point is 0. That is, if we take any point along this, what is that equatorial line, any point along this equatorial line, the potential at any point on this line is always 0. That means, so we do what is that, it doesn't require any work done. That is, no work is required to be bring that point from infinity to any point here on this line, along this line. No work is done, or no work is done on that positive charge, or no work is done by the positive charge. If the point is moving along this equatorial line, that is potential is 0. Remember, so potential at any point along the equatorial line is 0. Potential at any point along the axis of dipole is this value. There is a value. It is not 0. Kp by R square. Look at the difference. The potential at any point along the axis is some value. The potential at any point along the equatorial line is 0. And the field at this point is this. And the field at this point is this. These are the mathematical expressions, very important. Using this mathematical expression, this is the one expression and other expression and one more expression and one more expression to estimate electric field and electric potential at any point along the axis of dipole and along the equatorial